Hi kiddos, welcome back. And what we're going to be talking about in this next video is the emission spectrum that results when electrons in an atom undergo relaxation. So this shows you an energy level diagram. And if you'll notice on the y-axis, we have energy level. So we could add, whoa, sorry about that. Man, oh man. We could add energy here. And let's give that another try. All right, so this would be energy on this, going up this way. And down here would be the nucleus with a particular nuclear charge Z. So the lower the N value, the closer we are to the nucleus. Now, this is showing the relaxation process. We're presuming excitation has already occurred. Relaxation is going from high N to low N. And in the process, electromagnetic radiation is given off. So some packet of energy h nu, which is related to the wavelength, right? And that's why we see different colors here in our spectrum. Now, each atom has its own unique spectrum, and you're going to see this in more detail when we get into some calculations, and that's because the actual energy for energy level 1 and 2 and 3 and so on is different for each atom, and that's because the nuclear charge is different. So, gives you an idea of why we're seeing the electromagnetic radiation, the spectrum here. Now, if you are in IB, you need to be aware of these different series. The Lyman series ends at n equals 1, the Balmer at n equals 2, and the Paschen at n equals 3. Now, if you look at this difference in energy, so I have a delta E equal to, in this case, energy level 1 minus energy level 2. We always do final minus initial. All right, so we get a delta E. If we take the absolute value of that difference in energy, that's going to equal the energy of the photon that's emitted, right? Because photons can't be negative energy. They always have to be positive. So we have to take the absolute value of that difference in energy. Now, once we did that, we can start seeing some relative relationships in here. So let's take a look here. As you increase the difference in energy, you're going to increase the energy of the photon. That means you're going to decrease the wavelength. Okay, it's going to be a shorter, higher energy wavelength. So in the ultraviolet, we have, and this, my picture might be not quite to scale, but it gives you an idea. The ultraviolet is for the Lyman series because these energy differences are larger here. Now, do you notice as we go up in N value, the difference, the distance between these two, the difference in energy, remember energy is on this Y here, gets smaller and smaller and smaller. And you need to understand that concept. The energy levels are said to converge. So that means as we get up to transitions at higher N values, we have a smaller energy, and that would be in the IR for the Paschen series. So this would be low energy, long wavelength. This would be high energy, and it would be short wavelength. Now, what we're going to see when we look at the spectra in our classroom, I'm going to show you the different gas bulbs of, say, hydrogen and mercury and oxygen and neon, and we'll look at them through special glasses, and it will enable us to see the Balmer series. Now, these lines that we see in here are going to vary. So the number of lines and the colors of the lines will vary with each element. And that's because each element has its own unique electronic structure. Okay, so to use my loose analogy, the electron playground is going to be different for each element. So that means these energy values will be different. So that means the energy of the photons will be different, and hence the wavelengths will be different. So that's why atomic emission spectra provide a unique fingerprint of each element. Now, I want to show you another representation of this in the next figure. It's not my favorite figure. It does show a couple of interesting things. This is called a shell diagram. And I'm sure you can tell by now that I'm not thrilled with this shell diagram because it implies that electrons orbit. We don't know how electrons move. All we can talk about is distances from the nucleus. So if that center dot, and this is obviously not drawn anywhere near to scale because most of the atom is empty space. All right. But it does show, this again shows the Lyman and the Balmer and the Paschen series. Instead of just showing you as lines, I wanted you to see that these are energy shells surrounding the nucleus, and its electromagnetic radiation is emitted when electrons go from one energy shell to another energy shell. So I just wanted to give you an indication of a different representation. So that's n equals 1, n equals 2. You notice that energy levels converge as they get further and further from the nucleus. Okay? All right, that's it for this video. So until I see you in class, this is signing off.